Introducing aPriori.
Hello, and welcome to Design-to-Cost versus Design-to-Value, a case study. My name is Matthew Hinshaw, and I am a senior technical consultant here at aPriori. I work on the implementation team, and I've worked with dozens of customers across a slew of use cases and industries during my time at aPriori. This presentation, as I mentioned, will focus on the concepts of design-to-cost and design-to-value. We'll start with an introduction of these terms and some common examples of application. Then I will introduce our case study and walk through a number of design iterations that explore the relationship between design to cost and design to value. So before we get started, why is this important? Why do these concepts matter? Well, roughly 80% of a product's cost is determined during the early stages of the design cycle. So applying these concepts early is critical in impacting the eventual cost of a product. And approaching these ideas once the product is already through those initial design stages could have a limited impact. Let's start with the concept of design to cost. The core concept behind design to cost is designing a product with a focus on hitting a specific target cost. While there are many ways to reduce cost, this may include removing functionality or discarding expensive features. There are lots of examples of products that are designed with the intention of hitting a specific cost. Let's say we're designing a pop-up toaster. I can go on the internet right now and purchase any number of pop-up toasters for, say, $30 or less. So if we're designing a product that is going to be cost competitive in this crowded market of basic pop-up toasters, naturally we have to aim for this common price point. This doesn't mean we completely strip the product of any and all value to the end user, but we may need to make decisions to remove or limit functionality in order to hit our target cost, such as you likely won't be able to start this toaster from your phone. For that matter, phones and computer monitors can fall into this category as well. Well, there's a huge breadth of phone and monitors in terms of price points and capabilities. If we are designing these products for the low-cost end of the market, we likely have to be very judicious about what features are included in order to stay cost competitive. Design to value, on the other hand, places the emphasis on features that add value to the customer. Additionally, of course, we also want to remove features that are not adding value to the customer. Depending on the application, this could mean a decreased focus on final cost of the product. Let's take the International Space Station, for example. Not to say that there is no focus on target cost, but for critical components that are keeping the astronauts on the ISS alive, I imagine there's a much stronger priority put on product performance, reliability, and survivability of these key components in space. Performance motorsports is another good example. Now, I know there have been some changes recently with respect to budget caps and things like that, but similar to the ISS, the focus for these vehicles is on performance and the value each component adds towards winning races. So now that we've defined these two terms, let me introduce the case study for today through which we'll explore these concepts. So let's talk for a second about in-house manufacturing. I'm sure for many people watching this video, many if not all of your companies have some sort of in-house capabilities. So while I don't have access to a machine shop or weld booth or something like that, I do proudly have a bit of in-house manufacturing in my apartment in the form of this 3D printer. And as with anyone who has the pleasure of owning a 3D printer, I am constantly looking for new projects and applications for my printer. As a consultant at aPriori, I'm on the phone a lot with customers and naturally have a headset. As work from home became the norm during the pandemic, I realized I needed a place to hang my headset so that I wasn't just throwing it on the desk when I wasn't using it. To that end, I put my in-house manufacturing to good use and made the headset hanger you see here in the images. For our case study today, I would like to explore with you how we could bring this prototype headset hanger to market through the lenses of design to cost and design to value. Before we get started with evaluating designs, first let's define our design specifications. The overall product goal is to create an ultra low-cost headset hanger that easily attaches to most desks. With a lot of people working from home or working in a hybrid situation, we have a broad potential market, and our product can help anyone struggling with limited desk space or wanting to organize their working area. From a design parameter perspective, through some research of typical desks and headsets, we want to support any desk up to 1 inch in thickness, support headphones that are up to 1 kilogram in weight and 1 inch wide, and while many headset hangers on the market use an adhesive to attach to the desk, a critical design criteria for us is not using any adhesive to make it very easy for our end users to position, reposition, and move the hanger to another desk or table as needed. Finally, based on how crowded the headset hanger market is, our price target for this product is $5. Let's start with our initial prototype design so we can get a sense of where we stand cost-wise right now. We'll stay with 3D printing as our manufacturing process to model the initial manufacturing method. Based on our market research, we expect to make 10,000 of these per year, so when analyzing this product, we will assume 10K annual volume. For this SLS, or selective laser sintering version, we're using nylon 12 as our material, as we determined through further analysis that this nylon satisfies our design weight capacity requirements. Let's take a look at our initial iteration within AP Design. So here I have the CAD file loaded into AP Design, and I've costed the part so we can take a look at the results. So as you can see on the left-hand side, I've put in the inputs I was just discussing: additive manufacturing, polyamide 12 or nylon 12, and an annual volume of 10,000. And by running this part in AP Design, we can get cost and manufacturability feedback. So we can see here that we don't have any design guidance. AP Design isn't picking up any DFM risks or warnings we need to dig into for this manufacturing method. We can see things like the cycle time for the overall process, but really what we're looking for down here is the breakdown of cost to get a sense of where we're at the moment. So if I go into the cost results, I can not only see overall cost, see we're at almost $13 at the moment, I can see the breakdown too. And within our breakdown, we can see that material cost really dominates the cost of this part at the moment, which, given we're running an additive process, typically relatively efficient around material, this makes sense to have a high material cost with respect to the rest of our costs overall. That being said, though, $12.72 is still very high compared to our ideal target cost of $5. So we're starting from a point way above that target cost and indicates we need to do some more work to get to a design iteration that works and fits all of our criteria. Within Design-to-Cost and Design-to-Value, we can further consider two sub-approaches while making our design changes. We can make changes specifically to features on the design, or we can take a look from a manufacturing method perspective and likely design changes that are required as a result of changing our manufacturing method. With both of these throughout the process, we'll use aPriori design to generate cost implications and manufacturing implications of each action and use that to make data-driven decisions. Let's start with the lens of Design-to-Cost. So again, here we are considering design changes with a focus specifically on hitting that $5 target cost. For our first design iteration, let's focus on changing the features of the design, and we'll try to tackle some low-hanging fruit. An easy change here is to reduce the thickness of the hanger, as well as the length of the legs that slide over and under the desk. Less material, of course, leads to lower material cost, as well as faster cycle times, as with selective laser sintering, you just have less motion of the head as you're laying down material. We can keep all other parameters of the simulation the same, and again, run the part through aPriori design. Through this analysis, we could see a meaningful improvement in cost based on this design iteration, from over $12 on the previous iteration down to between $7 and $8 for this particular design. Again, though, this is not quite at our $5 price point that we're trying to hit. Additionally, I can tell you based on some initial prototyping I had done, shortening the legs does reduce stability of the hanger sitting on the desk because, of course, there is no adhesive. So I think we need to explore some additional possibilities through this design to cost lens. Let's dig into a change in manufacturing method next. So here we are maintaining the original design with the longer legs and thicker hanger, but switching from additive manufacturing to injection molding. Now, there is an annual volume consideration here in terms of where the cutover is to move from something like additive manufacturing to a hard-tooled process where you have that capital investment. And one of my colleagues, Cormac Eastwood, is going to explore these ideas further in his presentation on additive manufacturing. It'll be a great session to check out. For our purposes, though, at a volume of 10,000 parts per year, plastic molding may be cost-effective. To figure out, let's turn to AP Design again and see what this part looks like if we run it within plastic molding. So here I am with my part back in AP Design, and I have a new scenario specifically for injection molding. So my process group here is plastic molding, and I want to talk about material for a second. So previously we were running with nylon 12, which was satisfying our material requirements. But if I take a look at nylon within this list of materials available, we get a sense of a relatively high unit cost in terms of the cost per mass. Whereas if I look at something like ABS, I get a much more competitive price that would potentially lead to a reduction in cost for my part. So for this simulation, I'm going to choose to run with ABS instead of nylon 12 and see if we can get some cost savings through this change in material. Now, given we would need to run further analysis to make sure ABS as a material could support the weight requirements for our headset hanger, but let's take a look at the cost results and we'll see if the results here warrant digging in further. So now that I've run this as plastic molding, I get a number of important pieces of information from AP Design. In the design guidance section, I'm now getting design guidance on what I would need to change on my design in order to enable injection molding. So we can go in here into the details and start to look at what AP Design is giving us. So as we can imagine, the initial part was designed as an additive manufacturing part. So if we were moving over to plastic molding, we would of course need to put in draft angles so that the design can easily release from the mold during manufacturing. So this is expected, but we would of course need to make these changes. AP Design is also calling out radius issues. So here, if you've got a sharp edge, that means that you need a matching sharp edge in the mold, and that might be something we want to avoid in terms of stress concentration. So you might want to take a look at these as well from a redesign perspective if we're going to go ahead with injection molding. And lastly, we have an entry here around material issue. So the thickness of the part, which wasn't as big of an issue when we were running this through additive, is greater than recommended for ABS through plastic molding. So if we want to take this path forward within running this part and manufacturing this part as a plastic molded part, we really may want to dig in further into a redesign to reduce the thickness, maybe add some stiffeners, and approach this part from a different perspective given some of this feedback. But let's take a look at the cost implication and see if it would even make sense to pursue that. If we go back over here to our cost results, we get some great insight into overall cost. So whereas previously our iteration, our first one was almost $13, the next one was closer to $8 per hanger, here we are well under our target cost. Another interesting piece to note is that the distribution of costs has changed. So whereas for the additive part, 60-something% of the overall cost was locked into that material cost. Here, the driving factors are really labor and overhead, not necessarily material, because it's a relatively small part and the material is less expensive than, say, for additive. So by running this simulation, we get an understanding of design guidance, we get an understanding of cost results, and from an overall cost perspective, this looks like this could be a good path forward for this part. We can keep that initial design, likely need to make some changes to enable injection molding, but we're here under our target cost. That being said, if we think a little bit further about the design, there are still some clear issues overall that we haven't addressed through these design-to-cost iterations. The largest issue I see is really in desk compatibility. Yes, this design technically fits a desk up to 1 inch, but the stability as your desk gets thinner is most definitely compromised. It would be worthwhile now to consider this design from the perspective of what features or value add to the end user and see what results you generate. So let's dig in now to some design-to-value focused design iterations. So here we have a new design iteration that includes an additional hook. Many of our target consumers likely have multiple devices, even if they do not have multiple headsets. So a second hook may be value add for many users. It could also be used to hang the cord for their headset if they have a corded headset. For this simulation, we're keeping the learnings from our last design-to-cost simulation and running the part as injection molding with a material of ABS, as that seemed to be the most cost-effective from our design-to-cost iterations. Let's take a look at this part in AP Design. Once again, I've loaded in the new CAD file, set my inputs as I've done before, and we can take a look at the design guidance and the cost results. So if we start in design guidance, we're really getting a lot of the same information that were we to take this further, we still will need draft angles, consideration for radii, and of course the material thickness issue is still a challenge and might even be slightly thicker here with the way this iteration went through. So certainly worth further consideration there. On the cost side, however, we get to some interesting results. Our previous iteration was right around 250, and this iteration is as well. As I talked about a second ago, for these injection molded parts, they're relatively small, the material is not a major factor, and it's really the processing time that leads to the final cost that we see. That's the major cost driver. So because the thickness of the part is roughly the same as it was before, the material cost is only increased slightly with the additional hook, the overall fully burdened cost has not changed significantly. Certainly gone up a little bit, but not changed significantly because the overall processing, the time the part spends in the molding machine, etc., hasn't changed significantly. This is great insight. This is really good information we could take moving forward because in this iteration, we've added value to the user. There's another feature on this part that brings more value than just the singular hanger that we had before, but we have not significantly increased cost. We've been able to increase value without that increase in cost. This is good insight we can hold on to, and we can bring this with us as we think about some future iterations and how we can use this information to our advantage. Now, as we did with Design-to-Cost, we'll take a look at a little bit more of a almost manufacturing focused addition of value. So in this instance, we are keeping the initial design, but kind of changing the nature of the product and even potentially our target consumer. I propose here that we could create custom-made hangers based on the customer's specific headset and desk parameters. So we go to the consumer, they could put in how thick that their desk is, how large their headset is, and what they want to hang here. and then we could laser sinter parts out of aluminum and tumble deburr for a really nice finish. These hangers are specifically sized for each of our customers, so there's some cost, of course, associated with some design changes before we send these parts out. But unlike the previous designs, this iteration is really focused on customizability and visual appearance as means to give value to our end user. Of course, this all comes at a significantly higher cost. Compared to some of the plastic molding examples, a factor of 10x. We would need to perform further market research to understand if there's a market for this kind of bracket at this price point, and if it makes sense to take this further, because this really does change the nature of the kind of product we're putting forward. Maybe it's a good alternative, but perhaps it does not help with our overall goal of this low-cost headset hanger. So where does this put us? We've looked at design-to-cost examples. We've looked at some design-to-value focused iterations. Are these two really mutually exclusive? There are some contrasting goals potentially, but let's take a step back and look at what we've learned from these different iterations. We saw from the design-to-cost focused iterations that we can reduce costs through shrinking the part. Gonna restart on this slide. We saw from the design-to-cost focused iterations that we can, of course, reduce costs through shrinking the part footprint to reduce material costs used, or I'm going to restart one more time on this slide. This one's a little challenging, evidently. We saw from the design-to-cost focused iterations that we can, of course, reduce costs through shrinking the part footprint to reduce material used, but the largest reduction in cost came from the material change and switching to injection molding, which, as we saw, would likely require some design updates to make the design compatible with injection molding. From the design-to-value iterations, we saw how multiple hooks could add value, as could customizability of the hanger. However, the customizability of the hanger really speaks to a larger consistent problem with nearly all of these designs, which is the current design just doesn't support multiple thicknesses of desks very well. With our target consumer likely encountering a variety of desk thicknesses, this feature would really add meaningful value to the product, but we need to be able to still hit our target cost. So let's see how we can bring all this feedback together. Enter iteration 6. Here we are taking a meaningful jump forward in terms of functionality, where we add a thumb screw and a cap feature to specifically support using this hanger on multiple desk thicknesses. In doing so, we also do away with the stability issues that kept the legs on the hanger itself so long, and we can shorten those up to remove unnecessary material and costs, like we did in one of the design-to-cost iterations. Running this assembly in AP Design and ABS, including the thumb screw component, which is likely an off-the-shelf purchase, we get to a cost just above our target. So here we have major improvement in value, but we have made the product more expensive as a result of bringing this additional value to the end user. Again, we kind of see this contrasting behavior between this design-to-cost focus and design-to-value focus. But let's try to take this a step further and try to leverage some insight we can get from AP Design. Because we can run quick design iterations in AP Design, let's try some alternate materials. We know from our previous iterations and analysis that nylon 12 is a suitable material for the weight requirements for the design, but we shied away from that because it looked like the material cost itself was significantly more expensive than ABS. But let's run some iterations and let's take a look at using nylon 12 in our latest design iteration. When we run this, it turns out even though nylon 12 material cost-wise is more expensive than ABS, the processing parameters are such that the cooling time is meaningfully shorter. So by switching to a more expensive material on a cost per mass perspective, overall, we are actually achieving cost reduction on the part. For small parts like this in injection molding, again, the cost is primarily driven by the processing time, not the material cost. We learned that from one of the design to value iterations. So the end result is a final product, design iteration 7, which has a cost significantly lower than our target cost, but still maintains the flexible desk thickness feature, which is adding value to the end user without compromising on cost. So if we take a step back and look at the trajectory of this design, this is where we end up. We started with our initial prototype at a cost way above our target and worked through a number of design to cost focused and design to value focused iterations to understand how these decisions impacted cost. We finally landed on a design that brings meaningful value to the consumer above and beyond the initial design, while still coming in well below the product target cost. We did that by considering the outputs of our previous iterations that had a narrower focus and brought these takeaways together to influence and impact the final design. This really brings us to the fundamental nature of design to cost and design to value. These activities are not mutually exclusive, they really fall on a spectrum. Let's take a single product, say, a set of headphones. With an extreme focus on design to cost and just reducing cost, you can get to a very low cost but functional product like the earbuds on the left. With a focus on value to the consumer, you can get to an advanced, feature-laden, but much higher cost product like the headphones on the right. This is not to say that the earbuds have little or no value to the consumer or the headphones have zero regard for cost. Not at all, but the focus is decidedly different. Products may land on one end of the spectrum or the other and everywhere in between, but both concepts gives us valuable insight as we iterate through designs. AP Design lets you get cost and manufacturability feedback on those designs as you work through this process. So no matter where you fall on the spectrum, you can make data-informed decisions quickly as you reduce costs and add value through these processes for your customers. I hope this session was valuable and insightful, and thank you for joining.
aPriori, making profitability and sustainability a reality for a better world.